so picking up where we left off last time, we were looking at the anatomy of both a C program and its equivalent in Java over here, where we were reading in we were prompting the user, interactive input, we were prompting the user to enter in a number of miles and then to output the equivalent number of kilometers. So, to continue from there, we ended up by looking at reserved words, int, double, and return, that were basically in those programs. But now let's look at those in more detail in both languages. Those are called variables. Why are they called variables? Because they are things whose value can vary. Unlike over here in C, where we created a macro, an alias, that's not a variable. That's a constant because it'll go through my program and cut and paste and put that constant in there. Over here in Java, I've also created a constant with KMS per mile by using this final keyword. Final means that once you set its value, it can never be reset. In fact, it'll be a compiler error if I ever try to reset it. This is a preview of an assignment operator, but if I try to set it to, let's say 2 or something like that, it's going to be a syntax error. It's not going to let me reassign that. So in contrast to variables, these two things were constants. Their values cannot be changed, just like pi. Pi does not change. The number simply means that, there are consequences to this, that before you can use any variable, you need to declare it, right? And declaring it means you need to define its name. The technical name for that is its identifier and its type, right? And the three types that we're going to look at in both languages are going to be int, double, and char. Right? So int should be pretty clear. Int is short for integer. What is an integer? It's a whole number. 0, 1, 2, 3, 4, 5, but also in the negative direction. -1, -2, -3, -4, whole numbers, right? A double is a double precision floating point number. That means that you can represent fractional values. But both of these things are finite. Computers are finite. Have you ever run out of memory before? Yeah, why? Because you only have a finite amount of memory. But these numbers that go both directions, right, they're infinite. So how do we reconcile those two systems? Infinitely large numbers versus a finite computer. There are going to have to be limits placed on them, right? And we'll talk about those limits here in a second. Actually, yeah, wherever you declare a variable, is its scope, right? Right? The area of the code that the variable can be seen and is therefore valid, right? So scoping means that if I declare a variable here, right, then that means that it's good from there down to the rest of the scope. We haven't looked at any complex programs yet, but when we eventually have a loop, or when we eventually have entirely different functions or entirely different files, those are all going to be different scopes. If you declare a variable over there in that file, that's not necessarily the same variable over there in that file, right? You can use the same name, x and x, but they're in different scopes that can be seen, and therefore that's that variable for that scope. To show you what I mean by that with this very simple program here, what if I had declared these variables down here, right? Well, I declared them, they should be valid. In fact, after that line, they are valid. Miles and kilometers, there is no syntax error there at all. But up here, one line before I actually declared it, that's going to be a syntax error. That's going to be a compiler error. Why? Because it doesn't know what miles is because you have not yet declared it. Remember, linear control flow, it starts at the top, we read a program top to bottom, left to right. I've not gotten to the point where I'm declaring this yet, so it doesn't exist. Right? It's not within the scope. It can't be seen. Right? Let me go ahead and restore that so that it actually works. Okay? All right. So let's take a look at those three variables, basic types. Basic types. And by the way, yeah, I'll get to setting variables here in a second. An int is a 32-bit 2's complement integer. Right? Don't worry about the details there yet. Right? Well, we do want to know what a bit is. What is a bit? It's a 0 or a 1. Right? 8 bits make a byte, 4 bytes make a word, kilobytes, megabytes, terabytes, or gigabytes, terabytes, then what? Petabytes, then what's after that?
I don't think you made it.
Oh, there's a name for it. Yeah, certainly they have it over in the Holland Computing Center, High Performance Computing Research Center. They've got petabytes of data on a daily basis, and therefore on large RAIDs where they have many, many different servers and different hard drives, the collective amount of memory there is definitely in that range. Right? 2's complement, don't worry about that. That's the hardware representation. When you eventually get to a hardware class, that's going to be important for you to understand because there are limitations to that. But for now, let's just understand the limitations that we'll be encountering. You can represent 0, negative, and positive numbers in the range. And here I'm going to copy it because I'm not too good at, there we go. In fact, I'm going to put this into math mode. Actually, no, I'll put this into math mode. There. Up to, all right. I'll just replace that with there. Oops. Get rid of that and get rid of that. I'm typing, behind the scenes here, I'm typing LaTeX, which is a typesetting system for mathematical formulas. If you're interested in it, I'll show it to you sometime, but otherwise, let me go ahead and replace this L dots. There we go. Dot, 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 right? So don't worry about these for now. Just know that there's a maximum value that you can represent. What value is that right there? Well, it's kind of hard to read because we need commas there. You can't put commas in an actual program because commas are reserved for lists of things. So I will go ahead and put a comma in here, and comma in here. So what's the maximum value that you can represent with an integer? 2.147 billion something, right? And change. All right, well, what about in the other direction? You can represent 0, and you can also represent numbers to negative 2.147 billion. But note here the last value, 8 and 7. Why are they different? What's in between these two numbers? Positive, 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 negative, 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 coming to meet in the middle. What do we have? 0, right? And so it's got to be represented somehow. So we take away from the positive side and get that, right? Why is it like this? Well, because we have 32 bits. A bit is a 0 or 1. The first bit is always the sign bit. Is it negative or is it positive? Right? 0 for positive, 1 for negative, right? Fine. We're left with 31 bits. 2 to the 31. Why 2 to the 31? Well, if I told you that you had 5 digits, what's the maximum value that you could represent? 99999. 1 less than 10,000, isn't it? 900 or 100,000. There we go. 100,000. I'm off there. 100,000. Well, computers don't work in base 10 because they don't have fingers and toes. Instead, they work in base 2. So if I gave you 31 bits instead of 10 digits, or whatever digits I said, then you have a maximum value of 2 to the 31st. Why minus 1? Because we start at 0. Likewise, in the other direction, negative, because we're taking away that 1 bit for the sign bit, 2 to the 31st. So what happens when you're dealing with numbers that are larger than that?
You double or you get integer overflow.
Oh, integer overflow. So let's talk about that. X is equal to, let me go ahead and copy that value because I don't want to write it out. There we go. There, that's perfectly fine. But what if I go ahead and do x is equal to x plus 1? And then system.out.println x.
Go back to negative.
Well, let's find out, right? So what happens when you run out of digits? If I gave you 4 digits, 9999, right? So 9,999, and you added 1, but I'm not allowing you this 5th digit over here. What happens? 10,000, what happens to these 4 digits over here?
0.
All zeros. So 0, but now our sign bit is 1, and then 2's complement magic here. What ends up happening is something a little bit different. It rolls back to the other number. Why? There's that number right there, right? So it's not a line. We think of the number line, negative values coming up to 0, going up to positive. We don't think of it, that's not how a computer works. A computer, it's a circle. So if you keep adding, keep adding, keep adding, keep adding, what happens? you eventually come back to where you started, right? Yeah.
There's a funny kind of reference to that in an old civilization.
Nuclear Gandhi.
Yeah.
Yeah.
This is called overflow.
The integer would overflow, and so he would go from super peaceful to
The craziest
To,
dude on earth.
to super aggressive, right? So yeah, think about the recent think about the recent lottery issues or lottery numbers that you've seen. If you ever go to a convenience store, they only have 3-digit numbers, right? 999. So what happens there? Well, I've seen people just take a piece of paper and tape it over. It's over $1 billion or something now, right? So we have what's called overflow. If you have a glass and you fill it with water, it gets too big, it gets 2.147 billion, then what happens when you add another little bit of water? It overflows, and it overflows back to where it began, right? So those are the limitations of integers. What about doubles? Double is a 64-bit, and here's the technical term, IEEE 754 floating point number, right? Now, if you're really interested, you can go and look up the standard for IEEE 754, and you can read all 500 pages of it, or whatever it is, right? What happens, and how is this number represented? What happens in every single possible situation, because it's a big, giant standard. For us, just understand that the limitation is that you can represent any number, any very large magnitude, but with only 16 to 17 digits of accuracy. Right. So I can represent pi out to about 15 digits because I need 3 out front, right? And after that, who knows? It's just garbage. It's just garbage data after that. But that's pretty much enough to do anything in this course, certainly. And certainly that kind of accuracy, that kind of precision is probably good enough for most applications. Both limitations can be overcome with software. Right? There are, in both languages, there are libraries that allow you what are called arbitrary precision digits. So you could bring in like, big integer, big decimal in Java. In C, the go-to library is GMP. That's what it is. GNU's multi-precision library, right? GMP, whatever it was. And you can add, if you have a really big number and a really big number, you can have a bigger number. How does it work? It simply allocates more memory to hold it. Right? And now this limitation is gone, but now it's the limitation of the actual computer. If you only have so much RAM, then you're going to run out eventually anyway, right? So it only, kicks the can down, and of course our universe is finite too, and only 5% of it is actual matter, and the rest of it's dark matter and dark energy. So can we ever actually use it? No, right? So there's got to be a limit somehow, because technically the universe is finite, but mathematics is not, because it's an abstract concept. Finally, chars, right? Char is a single character in both languages, but in C, it is an ASCII text value, right? In Java, it is a full Unicode value, right? So what do I mean by that? Well, let me come over here and let's look up at the ASCII text table.com, ASCII-table.com. This is very old. This dates back to the 40s, I think. 19 something. Do they have the history here? 19, nope. All right, I don't know when it was, but they came up with this ASCII text table. There are lots of it was designed with a lot of little tricks. But if you've got a single character, for example, if you have a capital A, that has a corresponding decimal value, 65. Over here, if you've got a lowercase a, that has a corresponding value of 97. Right? You can represent values from 0 all the way up to 127. Right? That's because it uses 1 byte, actually 7 bits technically. But that's your limitation with ASCII, right? And because it's very, very old. They just took the keyboard, the QWERTY keyboard, the QWERTY typewriter at the time and said, we need all this stuff in there. So, for example, say what? 61, thank you. Actually, I thought it dated back to Eisenhower.
Oh,
okay, all right. We also have a value 0 to 9 here, the actual characters, not the numbers, because 0 to 9 are actually control characters here. 0 is the null character. It always comes first. You can make your console ding with this bell. If you print out this bell here, it'll just go dunk, dunk,
Pretty sure that
right?
was named from the bell that
Oh, was it? Okay.
I'm not actually sure.
All right. If you do it on my Mac here, it will definitely go dunk, dunk, dunk. Backspace, etc. There's a tab character. Where is it? There's an inline character, which would be, there we go, 10. Where's tab? Does anybody see tab? 9? A horizontal tab, there we go. And then the space character, and then punctuation characters, followed by digits, followed by operators, followed by the alphabet. Capitals come before lowercase, and it goes A to Z. Numbers come before letters. This is the ASCII text table, and anytime that I say lexicographic order, it's according to this table. If you order things according to this table, it's almost alphabetical. A comes before B, B comes before C, et cetera, but it's not going to be alphabetical because capitals and lower cases, they're different. Capitals will always come first. Therefore, zoo, capital Z, zoo, will come before lowercase a, apple. Right? So it's not alphabetical, it is lexicographical. Right? Yeah?
Is this like how they order stuff when you like sort through the file explorer?
Potentially. If it's case sensitive, then yes. If any case sensitive search will be according to the ASCII text table here and its extension Unicode. Right? So we only have 127 characters here. There is an extended ASCII character set here that allows you diacritics and little drawings and such. But Unicode is where it's at because Unicode has millions of characters. CJK fonts, Chinese, Japanese, Korean fonts. Ancient hieroglyphics from Egypt, right? Cyrillic, every language, every natural language that there is. One thing that they rejected though was Klingon, because it's not a real language, right? But in any case, what you know Unicode today from the emojis and text stuff, right? It was started in Japan. They had all these emojis, and they wanted a way to represent them universally. Unicode, smiley face. There we go. And each and every single one of them is exactly like the ASCII text table in that they have a number, right? So let's go ahead and right here, grinning face. It has a number 1F600, right? So that's a much larger number. It's hexadecimal. And so you have, I think, 1.6 million possibilities, and only a fraction of them have been taken. You can actually write up a proposal to introduce another emoji or another emoticon or whatever they're called. They were originally called emoticons, I think, right? And then now they're emojis, right? But that's natively supported in Java. It is not supported in C unless you bring in a library. But don't do it like in Java, right? Like last time, don't have a variable name, a number of hamburgers with the actual hamburger emoji, right? Because you're crossing your fingers there and hoping that it works across all systems, and it's probably not going to be the case.
And they want to look at you with cheese ass for a second.
It'll look weird, definitely, right? So those are variables in both languages. By the way, both languages support other variable types. I'm only giving you the tip of the iceberg here because I'm not going to spend a week or two on each and every single variable, on all the variable types. With Java, you also have floats, you have byte, Boolean, et cetera, et cetera. We'll get to Booleans in both languages later. But both languages support floats. Floats are just less accurate, doubles. That's why we call them doubles. You have a float, which is a 32-bit number, and a double, which is double that, 64-bit. Right? It's just less accurate. You only have like 7 to 8 digits of accuracy instead of 16 to 17. So there's not even really a use case in this class to use them. I will mention, though, there are plenty of use cases out there, especially in game programming. Game programming, the default is going to be a float instead of a double. Why? Because it's smaller, more efficient, and it's accurate enough for any screen's pixel. Right? Just like a double is probably going to be accurate enough to calculate pi or the circumference of the known universe out to 16 decimal places or whatever it is, right? It's accurate enough, and that's actually an engineering fundamental, right? I'll always ask, What's better than good? Good enough, right? Exactly. You only typically engineers will when you engineer to spec, that means that you're meeting the minimum possible spec, right? And so we're doing just fine here with doubles or floats, right? All right, so let's talk about input and output, or output, I/O, right? So let's look at C first. C. C. Output in C is done with printf. The F stands for formatted or formatting, right? You can provide any formatted string, and it will print to the standard output. What do I mean by the standard output? Well, if you're coming from a purely consumer point of view, what does a consumer look at a computer and think about? They think about a graphical user interface. They think about windows, and they think about buttons and stuff like that. That's not what computers started out with, and that's not what power users use. By power users, I mean us, real computer scientists. Real computer scientists work at the command line. Well, when it doesn't stop most of the time. It works at the command line, right? And over here in the console. That's what the standard output is. There's also a standard input. What do you think the standard input is?
0.
Well, you have a bunch of input devices, right? You have a mouse, you have a trackpad, you have VR inputs, right? The wands, etc., right? Well, what is the standard input? The oldest input, right here, the QWERTY keyboard, right? And that's what we mean by standard input. So, how is input done? Input is done with scanf, just the opposite, using the standard input. That is your keyboard. For both languages, you use placeholders. Or you can use placeholders, right? And the placeholders they indicate the type of variable to be formatted. Right? Indicate. Right? I'll change my spellings later on if I can, otherwise not that big of a deal. %D is not for doubles, as the D would indicate, is for integers, right? That's int, right? There is a %F. It kind of makes sense because doubles are floating point numbers, is for floating point numbers, right? That is double, right? The only one that makes sense is %C, is for characters, right? That's the only one that makes sense. And there are reasons for this, because a double is not really a float, it's a long float, LF. And in fact, that's a gotcha. For scanf in C, you need to use %LF instead of F. All right, that's just a gotcha right there. Oops, sorry. Come on. There we go. Both printf and scanf use these placeholders. Let's go back to our kilometers to miles program and take a look at those placeholders that I put in there. And I said, magic for now, let's look at it later. All right, please enter miles. Well, I'm using scanf. So if I want to read in a double as miles, then what do? %LF. I read it into miles. What is this thing? We'll talk about that in a second. If you want to print something out and you want to print a double, %F, %F. Let's remind ourselves what it looks like and what it does. Right? GCC, kilometers per miles. I just heard it. It was a donk, right? That's probably the bell, right? A dot out. Please enter miles. I don't know how many miles I ran because I ran outside today, and so I ran 12K instead. And so I don't know what 7.5 it should be, maybe 7.5. Right, there we go. There. Okay, there we go. Pretty darn close there. So 7.5 miles is equal to 12 point and then change kilometers, right? What is the default formatting there? It's printing it out to 6 decimal places of accuracy. Right? That's the default. We can change that later on. For example, if I'm printing out currency, We don't print out $50.68 and then some fractional cents, right? We only print out to 2 decimals of accuracy. How can we get that behavior later on, right? So before we do that though, let's look at the consequence of not matching these things. For example, what if I change this to int? This is going to compile just fine with warnings. The warnings are going to say, wait a second, you've misformatted this stuff here. This is %f, but I'm expecting a double, but it's of type int. Right? Just a warning, just a warning, just a warning. Thank you very much, compiler, for warning me about this stuff. I don't know how to get that to go away. There we go. It'll still run, but there will be consequences to it. That's 7.5 miles. Is that an integer? Nope. So what is it going to do when it reads it in as a floating point number and then or as an integer? Oh, sorry. It'll probably work actually. Let's find out. Nope. Yep. Well, actually, in this case, it doesn't do anything at all. 0 is equal to 0. That's correct, right? But that's not what I entered, right? So let's go ahead and change a few things. For example, let's go ahead and say that this is an integer. Let's also go ahead and say that this is an integer and this is an integer. Those warnings will now go away. If I recompile this, okay, everything matches. But am I going to get the same results that I expected? 7.5 and only 11 kilometers now. So a completely different behavior for completely different mistakes. Why is it only 7? You said? Truncation. 7.5 is not an integer. Right? So this 0.5, what do I do with it?
Chop it off.
Throw it away. Right? And 7.5 becomes 7. It is not rounding. It is not rounding down. It's not rounding up. It's not doing any sort of rounding. It's just simply going to the decimal place, the period, right? And chopping it off right there and throwing it away. That's called truncation. Okay? And consequently, 7 and times whatever this is, truncated out, is going to be 11. Right? So let's undo all that stuff and get it back into the correct form. Right? All right, so if you use f, let's look at that. It'll probably complain about it, but it'll probably be right, okay, because I only need 2 decimals of accuracy here, and oh, no, it's not. Okay, so unexpected results. In C, if anything goes wrong, it's what's called undefined behavior. So if the C standard doesn't define what happens, anything can happen. Right? And the compiler writers are free to do whatever they want. Ignore it, make it 0, help you out and correct your mistakes, right? But they don't have to, right? And so generally what the compiler writers try to do, again, that engineering, the bare minimum, right? We wrote it to spec. What happens after that, who cares? Because that I didn't get paid for that, right? And anyway, so in this case, it was really weird. Let me go ahead and forget this ampersand right here first, for a second. GCC, yeah, it's gonna give me a warning about that. Let's run it again, 7.5 miles, right? 0, 0. Nothing catastrophic happened, but simply forgetting that one symbol completely changed the behavior of my program. It compiled, it ran. The compiler was warning me that something was wrong and I didn't do anything about it. It didn't have to, by the way, right? Warnings are, again, compiler things. The compiler writers are free to catch common errors and warn you about them. You are free to ignore them, right? So with great freedom comes great responsibility, right? Yeah.
Is there a reason to use formatted strings? In Java, you don't have to.
Yeah, in Java, you can use concatenation, right? And then it defaults to a different default. We'll talk about that in a second. But I did want to bring this to your attention that if you forget the ampersand, the compiler will warn you about that. We'll understand what that ampersand means later on. It's basically getting the memory address of this variable instead of the variable itself, so that you can pass it by reference to this function. Right? So for now, remember that scanf needs an ampersand, that is this thing right here, in front of the variable you want to read the value into. Right? Otherwise, by default, right, all doubles are printed out to 6 decimals of accuracy. Right? or precision. Accuracy and precision are not necessarily the same thing. All right, how do we change that? You can specify modifiers to placeholders to change their default formatting. And the format here that I'll give you is going to be %x.yf, where x and y are numbers. Right? So x refers to the minimum number of columns to print, and y refers to the exact number of decimal places to print. Right? So to understand that, let's look at an actual full example. And for that, I'm going to go ahead and use C over here. I'm going to go ahead and get rid of all of this stuff, just temporarily. I'm not going to delete it because I don't want to retype it. So what did I just do there? That was a quick key. Most IDEs will support this. If you are, it's going to be what? Control/. Even if you're in a language like Python that doesn't use slashes for comments, it'll still work. Right? So you can toggle it on and off here. You can do the same thing over here in, here, let's get rid of this. Toggle it on and off, right? For Mac users, it's Command/. You say Windows users, it is Control. Okay, Control. All right, so I got rid of this stuff just temporarily, right, so that I can go ahead and play around with my code here. Let's go ahead and define pi. So double pi is equal to 3.14159 ... and change. Right? Actually, should I be doing this? Should I be defining my own version of pi? No, just use the math library, right? Include math.h. When I do that, I don't need my own version of pi. Pi is defined in math.h to be m_pi. Hey, uppercase characters delimited by an underscore. That looks familiar. It's a constant, right? We use naming conventions to indicate the types of variables. We'll talk about that in more detail on Monday, probably. But otherwise, let's go ahead and print out pi. Printf, pi is %f, end the line, right? And I'll print out m pi. There we go. There we go. GCC. Here is our default formatting, 3.141593. Does anybody know how many more, what the next actual digit was? That doesn't look right to me, does it?
It's 2.
Yeah, it's 2. So let's print it out with more digits of precision here. How? By saying that I want 10 digits of precision. Both x and y are optional, right? They're both optional here. I didn't specify them. I will specify y, but not x, to get 10 decimals of precision. GCC. Okay, so now do we understand why it went up to 3? It rounded for me, right? So printf rounds, but only for printing. It didn't change pi. You can't change pi, right? Pi is a constant there. But for the purposes of printing, it went ahead and said, okay, you only want 6 decimals of precision. I'm going to look at one more, and I'm going to round for you, right? Yeah?
Why does pi work here without the ampersand?
Oh, because it's printf. Ampersand is only for scanf. Just like down here, we didn't put ampersand. Right? Okay. All right. Well, let's get more digits, or sig figs. Right? Sig figs, 20 digits of pi here. Or, you know what, let's go ahead and go crazy, 100 digits, or not 1,000. What do you think's going to happen? Well, remember, it only has 16, 17 digits of accuracy, right? So already it starts to get hairy down here, right? Count this out, and once you get to 16 or 17, it's no longer going to be accurate. So what does it do? Well, it does its best effort there. It puts in a bunch of garbage. It's actually probably accessing memory that's adjacent to that memory, and it's just taking whatever garbage happened to be there. And then finally it zeroes out at some point, right? And it can't fill, it needs to go down to the next line there, right? All right, so but remember, you only have 17 digits of accuracy. And that includes the 3, by the way. Right? So let's be more reasonable here, and let's go back to just 10 digits of pi. Right? But now I want to also print out the other place, or the other modifier here. Let's put a 20 in front of that and see what that looks like. Right? See? Pi is, and then we have a bunch of spaces there. So the behavior of this is, I am printing 20 columns minimum. Right? Well, there are 10 columns for the digits. There's an 11th one for the period, a 12th one for the 3. Where are the other 8 coming in? 1, 2, 3, 4, 5, 6, 7, 8. Right? It's printing out a bunch of leading spaces. If you want to adjust and justify and move around your formatting so that you have these nice little tables, you can do that. In fact, you can do it even further. What if it's padding it out with a bunch of spaces and then justifying it. Now I'm getting myself confused. It's justifying it to the right. So your right is over here. It's justifying it to the right. What if I wanted it justified to the left? I could do that, although I wouldn't see it because now all the spaces are going to be on the other side. So let's put something else in there. Yay. Oops. Gee, there we go. And run it. There we go. And you see that those 8 spaces are now on the other side because I'm justifying it left now instead. Right. You can also do things like, let's go ahead and go with int NUID is equal to 0, 0, 1, 2, 3, 4, 5, 6. Right, there we go. Unfortunately, I can't. I don't think I can compile this because you can't have. Oh, it does. All right. So you can put in leading zeros here, but I think that it gets hairy because that actually might be interpreted as a hex. So let me just go ahead and put 6 here. Your NUIDs, how many digits do they have?
9.
8. Your social security numbers have 9, right? And 2 of my children's social security numbers begin with a 0. How many people's NUIDs begin with 0? At least 10% of you should raise your hand. How many begin with a 0, 0, like this one? 1% of you should be raising your hand, right? Why? Because they're generated uniformly at random, right? So, and so the first digit, 0 through 9, each one has a equal probability, so 10% should have the 0. Right? What happens when we actually print this out, though? Printf, my NUID is %D, end the line, NUID. I'm going to get the default printing. Oops, we compile it first. There we go. Now, does that look like an NUID or a valid NUID? No. There's leading zeros. If you look at your end card, there would be leading zeros if you had them. If you go and try to purchase something, maybe that system was used to interpret it as an integer, in which case the leading zeros don't matter. Maybe that system was developed and programmed to treat them as strings, in which case the 0 does matter. And maybe 2 systems that have different design decisions, one's an integer and one's a string, are now trying to talk to each other, and they can't, right? So how do we resolve that as far as formatting goes? What I can do is I can say, I want you to print at least 8 columns on this integer. Okay, I will. But those 2 additional columns, they're spaces. That's not what I want. I want you to print zeros in lieu of that. So I'll put a 0 in front of that. There we go. And now I get my NUID that begins with 2 zeros. I'm not showing you this because it is super, super useful. I'm showing you this because this is the tip of the iceberg on all these features. If you take a look at the documentation for printf and scanf, you will see pages and pages and pages of really cool things and tricks that you can do with it. Right? For the most part, you're going to want to print out, say, currency to 3 digits of accuracy, if it's euros, or if it's 2 digits of accuracy for dollars or whatever. Yeah.
How is it differentiating between like a 2-digit number and the 0 and then the 8?
It's a good question. How is it actually parsing this out? The C folks that wrote the printf parser are going to say, okay, this is a placeholder because it's a % sign. 0, okay, that means that you want the leading zeros. Okay, 8, okay, then D, that's an integer, right? So it's going through and parsing this, and somebody wrote a very long program to take care of all the
So
possibilities.
it just does that with that leading zero? That's
Yeah,
the
yeah.
only use case.
You can add other things like, what is it? How do you do hex? 0x? I don't think that's correct, but we'll find out. Yeah, oh, wow. I should have used my luck on the lottery instead, right? But that's printing it out in hexadecimal instead, right? So there's a lot of different things that you can do. I'll go ahead and take away that though, right? So it parses it out and figures it out because somebody wrote a big giant program to take care of all those possibilities. Right? Question? Yeah.
Speaking of the currency thing, doesn't C have a,
There are currency
type for
libraries.
currency?
No, there are types for currency, but not standard ones. There is a built-in type in Java for currency, and so that is standard. And it's localized, so you can convert yen to dollars or whatever. We won't get into that though. All right, so let me go ahead and try to do the same thing over here in Java. What I'm going to do is I'm going to cut and paste everything. Right? All right, so mpy. There's no such thing like that. Instead, it's math.py. Right? So anytime that I see that, I'm going to replace this. So find m_pi and replace it with math.py. Replace all. Done. All right, so that fixed that. I'm going to show you some tricks. So printf, is there a printf in Java? Yes, there is. System.out.printf. So cut and paste all the knowledge that I just imparted on you, and it works exactly like it does in Java. Now you're probably more familiar with the basic input-output of system.out.println, hello world. Right? What does that do for me? That prints whatever is in there, and then it goes to the next line. Right? If you have variables, int x is equal to 42, int y or double y is equal to 10.125, right? System.out.println, hello world, and then I'll concatenate x, and y is, and then concatenate y. Right? That'll work just as fine as well. Oh, I forgot. I'm going to have to cut and paste, cut and paste, cut and paste. Right? Or am I? Let me go ahead and show you a trick here. Let me bring this up here so that I can show you the trick in its fullest. Int nuid is equal to 1, 2, 3, 4, 5, 6. There we go. All right, I'm going to go into what's called block selection mode. I'm going to not select text, a block. Instead, I'm going to select a vertical line here because I can start typing system.out. Oops, there we go. Dot. Come on. Alt dot. There we go. I'm going to go out of block selection mode. Very cool tips and tricks like that in your IDE. It is supported over here in VS Code. Off the top of my head, I don't remember how to do it. I'm on a Mac, so this is Option Command A. On a Windows machine, I'm sure that it would be like Control Alt A, something like that. You can try it yourself on Eclipse. Right? So let's see that this works. Right? There we go. We're seeing exactly the same stuff as before. Hello world, 42 concatenated, y is, and then concatenated. You can make it look as pretty as you want. X is blank, X, and Y is, add another space there, and get it just so. Printf is so much more powerful. Trust me on that. So you might have learned something like this, but printf is going to be a lot more powerful. Right? Another alternative would be system.out.print x. Right? So print without sans the ln means that it's not going to put in the end-line character for you. So you'll see that this doesn't go to the next line. 42 and then pi is, et cetera, et cetera. Right? Instead, you can always concatenate your own. Right? Now, instead of typing that every single time, that's why they added println. Right? How do we do input here in Java? Do you remember how it worked? We create a scanner reading the uncomment all of this because it'll still work. System.in. Oh, what does that stand for? Well, system.out, did you ever think about what that stood for? The standard output, your console. The opposite, system.in, that's the standard input, your QWERTY keyboard. Right? So we're going to create a scanner reading from this, the standard input, the keyboard, and then we're going to print out to the standard output. We're going to ask for the next double, et cetera, et cetera. So both of these languages, if I have something over here, I have the equivalent over here. Maybe it's exactly the same, right? Like all the variables, int, double, and char. They're exactly the same. Right? Basic input and output. It's all very, very similar as well. In fact, printf is available in both languages. Printf, by the way, is available in almost every single language. What about Python? Yes, right? It's just different syntax because they want to be different, right? Have you ever heard of f strings in Python? Formatted strings, right? So you end up going print and then f in front of your strings instead of printf. So it's kind of weird because they just wanted to be different. Right? But it's the same exact thing. Different placeholders though there. All right, with 4 minutes remaining, any questions? It's your first week of college, almost done, depending on you've got something in the afternoon. Your first hack, both C and Java, are due on Monday by midnight. Yeah?
Will we be learning HTML then too?
Probably not, no. Just C and Java. Yeah, go ahead.
Can you show the markdown slides again?
Sure. And everything else will be ported over here. I already made a commit for Wednesday, and in our weekly retrospective, I'll remind everybody of where the link is to get to all these things that I've been typing up here. All right. There was another question over yonder.
Oh,
Answered?
by the way, I was going to try to fix the GCC thing. That
Okay.
makes it
It fixed?
easier. No.
Well, that probably tells me that you don't have GCC installed. Maybe.
I installed everything that says GCC, so I don't know.
Okay. The question, yeah?
Why does Java not have like a native form of easy input? Like why does it have to use scanner?
That's just how they chose. Right? I mean, is scanf native? No, it's in the standard input output library, right? Is it native? Is it native in Python? Yes. What is it called? Prompt or something, or input? There's like an input function that you don't have to import, or something. So different languages, different things. Right? They wanted one because eventually what we'll do is we'll replace this input here with this is just a generic stream. Streams can be me slamming on my keyboard. It could be a file, right? So here's my input file. Here's my output file. It could be a network connection where somebody is sending me data over a network, and now that's my input, right? It can be any stream whatsoever. Likewise over here in C, same idea, but instead of scanf, there's fscanf. What do you think the F stands for in front of it? File. But we're not going to use that. We're going to use something different. There's also a printf. What does it stand for? It's going to print formatted to a file. Right. Yeah? %D is going to be the placeholder for an integer. If I have a single character, char initial is going to be my first initial here. Right, Chris, yay. How do I print that out? Hello. Hello, %C, and then end line, and then my initial. And I don't have time to run it, so I'll make sure it's in your notes. Otherwise, have a good first weekend.